the previous video, you already learned some limitations or the easy to use and straightforward number representation, which is sign magnitude systems. However, that's why we're going to learn the two complement numbers, which can solve the limitations. So let's just say we have n-bit systems. Then the position values for the most significant bits right now is -2 power n minus 1. So the only difference between this and the normal binary numbers that we have learned so far is that the most significant bit is now have the negative sign. So it's going to be 2 power n minus 1 instead of 2 power, sorry, it's going to be -2 power n minus 1 instead of 2 power n minus 1. Then the rest of n minus 1 bits have their position values as normal. So we'll see right now the position value is gonna be like this. So we have the first one, which is 2 power 0, 2 power 1, so on and so forth, up to 2 power n minus 3, 2 power n minus 1. And the most significant bit again here is -2 power n minus 1 instead of 2 power n minus 1. So let's give an example in 4-bit system, and it's going to have their position values of 2 power 0, 2 power 1, 2 power 2, and 2 power 3 minus. Then let's just have some bit sequence over here to see what they represent. So the first bit sequence is going to be all 0, second one is all 1, the next one is 0, 1, 0, 1, the next one is 1, 0, 1, 1. And if we're going to times their face values with their position values to see what they represent in decimal, we're going to have that one going to produce 0, so it's going to be 0 in base 10. The next one, which is special one, you'll see 1, 1, 1, 1, and we times with their position. This bit especially is going to bring -8. What is a special one? And when we add with all the others, one is going to produce -1. So in binary two complement systems, if you see the whole sequence with all ones, it represents -1. And if you see the sequence with all zeros, then it's going to represent 0. Then the next one will do the same things, and let's say this one times -8 is 0, this one times 4 is 4, this one 0 times whatever, it's going to be 0, this one is 1 times 1 is produce 1, and this one produce 5 in base 10. And the next one over here will have 1 times 1 is 1, 1 times 2 is 2, 0 times 4 over here is 0, and 1 times -8 is -8. We add them up, this one is going to produce -5. Okay? So this one is a summary of what we have said just now. Now, picking the next one is picking the two complements. So why do we care about picking the two complements? We'll see the number 5 that we see earlier is somehow relatively easy to produce, but the -5 is kind of difficult to take, or the -1 is difficult to take. So picking two complements is an algorithms in order to produce a negative version of existing bit sequence. Let's say if you have a bit sequence of -5, then how do you produce -5 from that bit sequence? Okay, so let's get this these are the steps. The step one is you first gonna flip the bit. If it is 0, you're gonna make it become 1, and if it is 1, you're going to make it becomes 0. Then the step number 2 is going to add 1 to the flipped bit sequence. So you add 1 over here, it's gonna be 0, 0, 0, 0, and the least significant bit is gonna be 1. So that one is the only one in that sequence. This one is at 1. And the resulting numbers will be the negative version of the original numbers over here. And these are the steps that I have set just now. I put them in text so that you can read them. So let's just take an example again that we have seen so far in 4-bit system. And this one is number 5. It's relatively easy to convert this bit sequence into number 5, but or number 5 into bit sequence. But it is relatively difficult to represent the -5 in computer. So this one is finding a representing for positive integers relatively easy, and this one is somehow more involving. So the solution is, can we convert from this bit sequence to that bit sequence? And the algorithm that we learn is taking the two complements algorithms. It's going to help us to do that. So how does it work over here? Let's say, so the step number 1, we'll just flip the bits. If you see 1, you'll bring 0. If you see 0, you're going to bring 1. If you see 0, you're going to bring 1. Then the next one is we're going to just add 1, or the bit sequence going to be all 0, then 1. And we at this bit produce 1, carry 0. At this bit produce 1, carry nothing. At this produce 0, carry nothing. And at this produce 1, and the carry nothing as well. And we can see right now that the 2-bit sequence are exactly the same. Okay, so if you start from positive 5, which is this bit sequence, you perform the step 1, which is you flip the bit, okay, and you perform the step number 2, which is to add 1 into it. It's gonna produce a result, and that result is actually the same bit sequence and represent the negative version of 5, which is negative 5 over here. Okay, so again, here is the example of how do we represent number 5 in binary sequence, and how do we convert that positive number 5 into negative number 5 by performing taking the two complement algorithms. The examples here is to represent the two complement numbers. You can just perform, let's say this is -3. How do we represent 3 and convert the the number 3 into -3? You should pause here and also work on this slide. That one is for the representation of 8-bit two complement numbers of 15 and -15 as well, and all, and how to find the two complement numbers or the given bit sequence. Okay. Now, if we use this two complements, then the 0 representation as well gonna be all zeros. And if we see, do we have the problems of having two different representations of zeros or not? Then let's say if we perform the negative version of that positive 0 by by taking the two complements. We'll see first we reverse the bits, all 0 become all 1. Then the step 2 is we add 1 into this, okay, add 1 into this, Okay, and then if we add 1, then it's also produce all zeros. Okay, and we note that we're going to discard um, um, the n bits carry, so it's going to discard the n bit carry. Then the resulting is also 0, which means that the negative version of 0 is also 0, which means that they have the same representation, so they don't have different representation for the 0 like the sign magnitude programs. So this video is long, so we're going to study the next part. This one is how can we perform the additions. Let's say the sign magnitudes were having some issues, but if we use 2 complement numbers, if we add 2 binary sequence, are they gonna work? But that's gonna be in the next video.